Okay, let's get started. Final session of the day. Putting the ASF to work for NASA. David Woollard will talk about the work that NASA, the work that NASA has been doing for the ASF and the role that the ASF is playing within NASA. Very curious to hear that.
Thank you. I inherited half the title to this talk from Justin Aaron Krantz. So it's putting the ASF to work for NASA is his part, and then I'm going to be talking about a project that we call OODT, or Object Oriented Data Technology. Government acronyms are an interesting thing. So it's an inherited title from about a dozen years ago now, but that's the project that we've moved into the incubator that I'm going to be talking about today. So I'm with a particular laboratory that's part of NASA. It's called the Jet Propulsion Lab. And within that, I work in instrument software and specifically science data systems. So I'm going to explain all of that in context of what we do at JPL, the kind of software we build. Spend about half the talk talking about just sort of general overview for everybody who's probably not involved in this domain. And then the rest of the talk, I'll be focusing on a couple of transitions that we've done in the last 5 years to first using a lot more open source software in our own development, and then finally making the transition to opening our software as open source as well. So the Jet Propulsion Lab is part of NASA. It was managed by Caltech, or established and continues to be managed by the California Institute of Technology in Pasadena, California. And really what we started out doing was building rockets and jet engines, but we transitioned to robotic space exploration fairly early in our history. And we were responsible for everything from the Explorer and Ranger satellites to Viking and Mariner and the interplanetary spacecraft. Today, what we're really focusing on largely is our Mars program, the rovers that we're operating right now, rover that we're operating right now, and as well as a lot of Earth observing systems. And that's particularly what I'm going to talk about today, is the structure of instrument software for satellites. So within context, what's an Earth observing system? What's a science data system, as I called it? So this is, in the very broad strokes, how we work at JPL. We work with a scientific community that wants to make some sort of observation of phenomena from space. The reason you do it from space as opposed from from ground or from aircraft is really you get global coverage and you start to map trends. You have really fast repeat cycles, so we can cover the same bit of the Earth, on something like a 16 or an 18-day repeat cycle. So we can build these great, interesting maps of trends and phenomena like carbon dioxide concentrations, or soil moisture, or freeze-thaw cycles, all sorts of Earth measurements that are interesting for climatologists, for people studying weather phenomena, for people doing carbon dioxide concentration research, global warming research. And so what we do is really, a lot of it is really interfacing to the scientific community. But at the same time, we're the engineers who actually have to build these things. And so we end up interfacing with mission operations, so that's the people that give us our satellite telemetry and downlink from the spacecraft itself. So they operate dishes and track satellites and do navigation. We also interface with our science team who are coming up with new and interesting algorithms. And really what we have to do is build this system in between. And that involves not only things like data distribution technologies and cataloging and archiving technologies, but it also involves scientific modeling, high-performance computing. Increasingly, people are more interested in workflow-based approaches to their processing, so that we can incorporate more flexibility and dynamism in the actual scientific experiment that's being conducted. And so what you see is really a very complex software system that sits inside this entire frame. And at the same time, in the last 15 years, we've seen a number of interesting challenges. Like a lot of people here, we've seen the challenge of big data. One of the things that's happened to us is that the instruments we use are starting to collect more data. It means higher resolution instruments, it means better downlinks, but it also means larger data volumes. In the 1970s through 1990s, we collected maybe 2 terabytes of data for all of our space missions. And a new mission that we'll be flying in a couple of years is going to collect 32 terabytes a day. So that's the type of scale that we've seen. And like everyone else, internet-based delivery has really revolutionized what we're talking about in terms of data distribution problems. At the same time, within NASA, we've had a culture called better, faster, cheaper. And it basically means that we're asking you to do the same, if not more complex science for less money. And by the way, your failures are exceptionally public. So what we've really been doing a lot more of is a push for software reuse at all levels. The budgetary restrictions are forcing us to get pretty creative. As an example of the kind of budgetary shifts that we're talking about, I know it might sound like a lot, but it's actually a pretty difficult thing to put a satellite into orbit for $150 million US. To give you a counterpoint, about 10 years ago, just a single instrument that we would develop on a spacecraft that was worth $2 billion would get that type of budget. So workforce has shrunk a lot, and so is the actual price tag on what we're building. And so we've seen a lot of changing requirements, and we've had to figure out how to address these as software developers. Another interesting challenge that we've seen, and this goes again to the big data problem, is another project that we're working on called the Planetary Data System. And what this does is it's a federated data system that houses all of our space-based research, basically. So everything that we've ever collected from any of our interplanetary missions sits in the Planetary Data System. And it's housed across a number of different institutions and universities throughout the United States. And just like Earth missions, they saw a scale crunch as well, right? So I mentioned that by the 1990s, we'd collected about 2 terabytes of data, and this spike right here represents a single instrument on the Mars rover is called Highline, which takes high-resolution photographs. But the next generation of instruments will make this look quaint, right? So again, these are the challenges that we're facing, and how we chose to address this is with something called OODT, or Object-Oriented Data Technology. It's a research task funded internally at NASA, and it was started in 1998. And basically, it was, at its start, a software framework for sharing data across these distributed archives. And so, in 1998, that was a relatively revolutionary idea. Today, we have all sorts of examples of federated data grids, which is essentially what this was back then. And so, we focused on issues of data production, data distribution, and then data discovery and data access. This was really our core software product for all of these missions that I was talking about. And the framework looks a little bit like this. We broke it into 4 components and then bridges to external services. It's a service-based framework in which we focus on cataloging and archiving. So this really is sort of a data repository type service. Profiling services. This allows us to bridge different storage languages and mediums and describe this data in an XML markup. Our product service allows web-based delivery, and also a query service to glue all of these things together. And this was really the start of OODT back in 1998. There's a good paper that was published back in 2006 that really highlights a lot of